Hi everyone, I'm Merve Ulusoy from Hacettepe University in Turkey, and it's an absolute pleasure to have this opportunity to present our project, Cellformer Molecular Representation Learning via Selfies Language Models. In this presentation, I will introduce the motivation behind Cellformer, together with its potential impact and the methodology we employed to achieve improved molecular representation learning. First, let's take a moment to understand the broader context of molecular representation learning. So, traditional drug discovery requires substantial resources, time, and money, and to overcome these challenges, integrating advanced computational techniques is crucial. Representation learning, which is a strategy for generating compact numerical representations, holds great potential in efficiently exploring the vast chemical space and identifying drug candidates. Transformers, a popular architecture in NLP, allow us to automatically learn valuable molecular properties from large chemical libraries. And these learned representations can significantly enhance drug discovery and development. Currently, most existing methods rely on SMILES notations as the primary input for their models. SMILES is a widely used string-based encoding, but it has its limitations in validity, uniqueness, and capturing essential molecular characteristics. To overcome these limitations, we introduced Cellformer, a transformer-based chemical language model that utilizes the Selfies notation. Selfies offers valid, compact, and expressive representations, enabling concise and meaningful molecular understanding for various drug discovery tasks. Let's explore the methodology behind Cellformer. Firstly, we employed a self-supervised pre-training approach using Selfies notations of 2 million drug-like compounds from the Campbell database, aiming to learn their high-dimensional embeddings. Cellformer is built upon the Roberta transformer architecture. It utilizes byte-level byte pair encoding for tokenization and also focuses solely on masked language modeling during pre-training. And during pre-training, we conducted a hyperparameter search, training and testing various models. Based on the MLM task's validation performance, we selected the optimal pre-trained Cellformer model, which you can see the selected hyperparameter configuration of the model here. And subsequently, we fine-tuned the pre-trained model in a supervised manner using benchmark datasets from the MolecularNet platform for molecular property prediction. Depending on the task type, we incorporated a classification or a regression head comprising 2 linear layers on top of the pre-trained model. Now let's take a look into Cellformer's performance on molecular property prediction tasks. We compared it with other chemical language models and graph-based approaches using scaffold split datasets. As shown in this table, Cellformer outperformed all existing methods in the multi-label drug adverse reaction classification task, CIDR. This performance can be attributed to the use of Selfies representation, which accurately captures subtle structural differences between molecules. And this advantage becomes evident when comparing Cellformer with Camberta2, which utilizes similar architecture to Cellformer but SMILES representations instead. And in regression tasks, Cellformer excelled in predicting the aqueous solubility of molecules, ESOL task, outperforming all other methods. To visualize Cellformer's classification performance, we employed UMAP projections. These visualizations demonstrated Cellformer's ability to distinguish small molecules with varying molecular properties, even without task-specific fine-tuning. Furthermore, we conducted a use case analysis of molecular property predictions on selected compounds from downstream analysis datasets. For example, in the BBBP task, Cellformer accurately predicted the blood-brain barrier permeability properties of compounds such as fentanyl and bromocriptine, both known to impact the nervous system. Similarly, in the CIDR task, Cellformer demonstrated accuracy by correctly identifying system organ classes associated with the side effects of verapamil, which is a widely studied calcium channel blocker. And lastly, in the ESOL task, we examined metronidazole, a commonly used antibiotic for gastrointestinal infections. Although cell-formers predictions showed a 35% deviation from the measured value, it's important to consider the inherent variability in aqueous solubility calculations across different databases. For example, cell-formers prediction aligned more closely with the reported value in drug bank. These results highlight the strong performance and the potential of cell-former in molecular property prediction tasks. In summary, cell-former demonstrates outstanding capabilities in molecular representation learning with a significant potential for enhancing high-throughput drug discovery and molecular design processes. The utilization of cell-phase-based representation models offers a powerful alternative to SMILES-based chemical language models for encoding and analyzing complex molecular structures. Cellformer, including pre-trained and fine-tuned model along with pre-calculated representation of vectors for all chemical molecules, is available as a user-friendly tool on our GitHub repo. For more in-depth information, we encourage you to explore our paper, which provides additional details and insights. Lastly, I would like to express my sincere gratitude to the contributors of this project, Atakan Yüksel, Atabey Ünlü, and Dr. Tunca Doğan. Our work takes place in the Biological Data Science Laboratory at Hacettepe University. Thank you for your attention, and please don't hesitate to ask any questions you may have.